Hello, everybody. So I would like to introduce you to Adam Forsyth. He's a software engineer at Braintree, who is an active member of the tech and open source community in the Chicago Python user group. He's really helpful answering questions on Stack Overflow, as well as a regular speaker at meetups and conferences. Please welcome Adam.
Hi, everybody. I'm Adam Forsyth. Like you said, I work at Braintree. I'm a senior manager and engineering lead, and I'm also the community lead of the Braintree team that does sort of conference sponsorships and events and things like that. So this talk is what's new in Python 3.8, and we're just going to dive right in. There are a few things that aren't in this talk. First of all, certainly not going to cover anything like every single change. There's dozens and dozens of changes that I don't cover at all. And I only actually cover one change in depth, and about something like 9 in total if time permits. It doesn't mean that those other changes aren't interesting or important. In fact, some of them really are. There may be other talks about them here. Just that these are the ones that interest me personally the most. Second, I'm not going to talk about subinterpreters, which I was really excited to talk about. This was something that a lot of people thought was going to be a big, exciting new feature in Python 3.8, because at the C level, Python supports multiple interpreters in a single process, each independently running Python code. And PEP 554, and PEP stands for Python Enhancement Proposal, proposes expanding that ability to be available from Python code itself. And that would allow in-process concurrency without removing the global interpreter lock, also known as the GIL, that prevents Python from running multiple operations at once. Unfortunately, this feature has been delayed until at least Python 3.9. If any of that didn't make sense to you, doesn't matter, it's not in the talk. So if any of you were hoping that this talk was by somebody involved in the process of writing or releasing Python 3.8, I'm sorry, that's not me. I'm just another Python developer, sometimes, who follows changes in the language and likes to talk about them. I think this is probably my third talk about a new feature in Python. So there aren't any insights here. I have the same access to information that everyone else has. And finally, I won't be showing any C code. I've skipped most of the features that are only visible at the C level. And even for the ones I mentioned, not going to be showing any C code at all. So just Python. The current latest version of Python is beta 3. And that's the version that I'm using for all the code snippets in this talk. The next beta is coming out in just about a week. And the final release, which is expected on October 21st, is pretty soon. And after that, they're expecting roughly monthly bug fixes as needed. So keep in mind that while we're pretty late in the release process and not a ton is likely to change, a few details could change because it just isn't final. So let's start with the big one, assignment expressions. That's right in the title of the talk. Can I get a show of hands? How many of you are already generally familiar with assignment expressions, the new feature? Okay, great. So a lot of you who aren't familiar, I'll go over the basics, and then we'll talk about what assignment expressions don't do and all the cool new things that it enables beyond the obvious. So the most important thing here to know is that the operator used in assignment expressions, colon equals, is informally known as the walrus operator. And this is because the colon looks like eyes and the equal sign looks like tusks. And internally, within CPython and elsewhere, like in a lot of the PEP, you may also have seen these called named expressions, or might hear that in the future. It just means the same thing. So here's a few basic examples on the left side of your screen, of my screen. So at its very most basic, you can define a variable, here y, inside the condition of an if statement. If you want to reuse that variable, then inside the body of the if statement itself, or after. It doesn't have to be the whole condition like it is in that first if example. If you look at the while loop, you'll see that I put some parentheses around it and I take a sub-expression out of there and assign that to the variable. And so that I can use that in the body of the loop and still also use that value to check against a condition to evaluate to true or false in the condition of the while loop. You can also do it inside of a literal, as you see at the bottom. I can define y to be foo of x again, and then I can use that value immediately in the same literal to compute future values without rerunning the function or having to extract it onto a separate line. And on the right, you'll see what happens if you try and do any of this in Python 3.7 or earlier. If you use either the regular equals operator or if you use the new walrus operator, either way, you're just going to get a syntax error and valid syntax. So there's two of super basic, like most simple ways that assignment expressions are used in Python code. One is to get rid of extra lines of code that don't add to readability and just exist to add a variable name. The other is to get rid of duplicate code. So these are really two different sides of the same coin, because a lot of the reason that code gets duplicated or an extra line is added is to avoid the other. And you can see this in the example on the left. At the top, I have foo called twice in order to avoid having an extra line. And at the bottom, I only call foo once, but I have to have an extra line outside of my if statement, even though the y is only used inside. And on the right, you can see what I do in Python 3.8. I have only 2 lines here. The y is only being used inside the if statement because that's really where I want it. And I don't have to call foo twice. So while this is sort of nice by itself, can avoid extra lines or double computation, there are some really specific cases where this feature really shines, and we'll get into those in a few minutes. It's not just saving you typing an extra line of code. So, but before we get to that, I want to talk about where you can't use this. The carets here, the up arrows on the screen, are where Python would indicate a syntax error for each of these lines. The biggest set of cases, all the ones on the left, are where you would use a regular equals sign. So when you're doing a regular assignment to a variable, when you're doing multiple assignment, when you're calling a function and assigning a value to a keyword argument, where you're defining a function with a default value for keyword argument, or where you're giving an inline type annotation inside the definition of argument to a function. And actually, all of these work if you just add parentheses. So it's not really that these things can't work, that they're just not really useful, and it's confusing to allow them without the parentheses, so they're not allowed. It's really just about eliminating confusion. And then on the right, you can see a couple of more interesting cases. First, inside a lambda, you have to parenthesize them. This is to make operator precedence simpler, and is actually, again, you can just add parentheses around it and it'll work. And I think in most cases where you'd want a variable inside a lambda like this, you're going to have to parenthesize the expression anyway, so it's really not a big deal. The final one is the trickiest, and I think the most important to call out here, which is that f strings, which are used to sort of automatically format variables within a string, colon equals is actually already a valid sequence of characters inside them. So what it means here is the colon says use the stuff to the right of this to format this variable, and the equal sign says I want to format it out to the width that follows. So if I have that x colon equals 10 here, it's not assigning 10 to x. It's saying I want to format x, in this case 1, in a string 10 spaces wide. So this is the only case where you won't immediately get a syntax error, right? Instead, you're going to get the wrong behavior. So you have to really be careful here. And of course, just like all these others, you can use parentheses to make this work. Not saying you should, just that you can. So there are also some things that you can do with a regular assignment statement that you can't do with assignment expressions. I'm not going to show where the errors are in the assignment expression equivalent of these lines. I'm just going to show the working assignment statement versions because they're going to look exactly like the previous slide if I don't. So assigning to anything other to a name, like an item in a list or a dictionary or something, only works with an assignment statement. Multiple assignment, where you assign to more than one variable at a time, also only works with a statement. You can fake it with parentheses, but you really shouldn't because you don't need to. Iterable packing and unpacking only work with assignment statements. So if you want to not parenthesize things and you still want to split out a sequence into multiple variables or compact a couple of things into a single sequence, you can't. You can, again, fake some of these cases with parentheses, but there are actually now some cases of these where you just can't do it with assignment expressions. And also, you can't do an inline type annotation. So if I wanted to say that y was an integer with a type annotation and an assignment expression, I'd have to put that on a separate line, which then kind of defeats the purpose of the inline assignment anyway. So probably isn't that useful. An augmented assignment also doesn't work with assignment expressions. If I want to add to an existing value using an assignment expression, I have to do it explicitly by saying like y equals y plus 1 instead of using plus equals to do it automatically. So now let's get to my favorite parts, the cool things that you can do with list, set, and dictionary comprehensions and with generator expressions. So first, let's look at generator expressions and the example at the top of the screen here. This is a little dense. That's fine. You have a few seconds. I'm going to be talking about it. But also, if you don't get it, you can always look it up later. So if, let's say I have a file and I want to see the first long line in it, and if I find a long line in it, I want to print that out. I can use any to look for the first thing that matches a pattern within a sequence. And here I'm taking the line itself and storing it in the long line variable, and then using that value, checking if the length is over 100. And if it is and it matches, I now have that long line variable that I can call out inside the body and print out that line. Normally, to do things like this, you'd have to use an explicit loop rather than an inline expression like a generator expression. Second, let's look at a dictionary comprehension. This is very similar to a generator expression, except that it produces a dictionary instead of producing a sort of sequence of unknown length, an iterable of unknown length. Here I will have a few different names that I want to process. I want the keys to be lowercase version of the names and the value to be lists that happen by splitting the names on white space. And so what I can do is I can take the name and lowercase it and assign that to a variable with an inline assignment expression. And then I can take that variable and immediately use it and split it to create the value. So here I only have to call lower once, and I can still do it in a single nice expression. Whereas in previous versions of Python, I would have had to either use an explicit loop or I would have had to call lower twice. So this actually had an interesting change that goes along with it is unlike when you make a literal dictionary or call the dict constructor, when you use a dictionary comprehension, the values were actually evaluated before the keys, so it wasn't sort of left to right. So in order to make this work and allow you to like calculate something in the key and then use it in the value, they actually did change dictionary comprehensions so that the keys are calculated first and then the values. So it's just an interesting thing to note. So assignment expressions can also be really nice to avoid nested if statements. You can see here where I'm using regular expressions, which are a way to match strings against patterns. Regular expression.match returns none if there's no match, or otherwise it returns an index in a string and some other stuff in a more complicated object. So in Python 3.8, I can just use a regular if, else if, else if, else, and I can run each regular expression once, capture the result. If it's not none, use it. If it is none, go on to the next condition. But in older versions of Python, I couldn't do that. I couldn't use else if because I would have no way to capture the value of the regular expression match without running it a second time or using a separate line. So here you see that you end up with a nested if statement, even though that's not what you really want, just to get around that. And it rapidly actually ends up bigger in 2 dimensions. Not only is it longer because of those extra lines vertically, it's also wider horizontally because of the indentation that ends up getting added. So you end up with something that's a lot less readable. Yeah. So one final set of examples before I move on to some other features. First, assignment expressions allow you to compute subtotals as you go and use them in the next iteration of an expression or comprehension. So here, if I want to like sum the values from 1 to 4, and I want to do that and keep the track of the subtotals as I go, it's super easy with assignment expressions. I just define total inline, and then I use that in each subsequent member of the list. So I end up with 1, 3, 6, 10, just like I want, without calculating anything twice. So this is really, really convenient. And finally, at the bottom, you can see that I can actually use assignment expressions even in the filter part of a comprehension or expression. And what that means is that I can capture the result of some kind of test or a sub-expression within that test and then use that in the output in a way I never could before, again, without calculating it a second time or using an explicit loop instead of a comprehension or expression. So here, I'm just calculating the remainders of dividing numbers from 0 to 9, modulus 4, and only if they're non-zero am I outputting them into a list. So I get 1, 2, 3, 1, 2, 3, and 1 again for 9. Yeah, so one final comment about assignment expressions before we move on. A common problem with writing more complex expressions in Python in a single line is it can be hard to debug them without refactoring them out into multiple lines with multiple assignments to sort of get subvariables and see where your error is really happening. That refactoring process by itself can both introduce bugs and can accidentally eliminate the bug you were trying to find. So what that can mean is that you actually hurt yourself by trying to debug. Assignment expressions make that much better. because you can just insert them inline. You don't have to change the structure of the code nearly as much. And it can really make refactoring less invasive and those kind of problems more easy to debug. That's not my observation. That and several of the others that I've made on the last few slides originally come from Tim Peters. And they're quoted in the PEP 572 that defines assignment expressions in Python. So that's it for this feature. It's definitely the most interesting language change for me, and I think for most people. From here on out, I'm not going to spend nearly as much time on each feature, so we can get an overview of a number of different changes. I'm going to try and get through 7 more, but we might have to cut a couple due to time. So let's talk about positional-only parameters. Many of you may know that by default, you can specify parameters to a function either with or without names. When using names, they can be in sort of any order, but they have to be after, to the right of, any non-named or positional arguments. And this leads to many different ways that you can call a function, and to the names of those arguments always being exposed to the caller, whether you want them to be or not. So as you can see in the top example, with the way I've defined foo, there are many different ways to call it, with different numbers of positional arguments, different numbers of arguments specified by names, and even different ordering of those named arguments. And they're all equivalent. They all return true here. It returns true when you compare the results against each other. And in Python 3, there's an additional feature, which you'll see in this function definition. You can put a bare star into the argument list, and that means that anything to the right of that star has to be a keyword argument. You could only use it by name and not by position. So if I try and call foo with just 1, 2, 3 as the arguments without specifying C by name here, I do get an error. And internally, within CPython, many built-in functions allow you to do the opposite. They only accept parameters by position and not by name, so that they're unambiguous in order and those names aren't exposed out to the caller. And so now with Python 3.8, you can do the exact same thing in your Python code. Similarly to how we use a star to say keyword-only arguments, we can use a bare / to separate positional-only arguments from others. So if you look at the very first line there, you can see I'm defining foo with still 3 parameters, but this time A is before the slash, meaning it's positional only. I can't refer to it by name. B is in between the slash and the star, meaning it can be positional or by name. And then C is after the star. And then if I try and call foo with that previously valid way of giving names for all 3 arguments in a crazy order, that's just not valid anymore. And one of the nice things about this is the type error you get has a great error message, way better than a lot of the ones I see when writing Python code. It tells you very, very specifically what you did wrong, which is awesome. So if you're designing an API and you don't want to expose your method names, or you want to make sure they're called in a certain logical order to help people think about your API, you can now do that way more easily by requiring arguments to be positional only. And it gives you just more flexibility and more knowledge about how your users are going to use your API. So next, let's talk about f-strings. These were added in Python 3.6. We've mentioned them a little bit already. And they let you specify expressions to evaluate, format, and interpolate into a string right in line and instead of having to call a separate function. So it makes them much more sort of left to right, easily readable. And you can use a colon inside them to specify a format. Here, I'm printing out math.py, formatted at fixed width to 2 digits after the decimal place. So as you can see, it prints out math.py equals 3.14. The new thing in Python 3.8 is what you can see at the bottom. I can stick an equal sign before the colon. I know there's a lot of equal signs and colons here, but this is totally different than what we talked about before. Either to the way the colon equals was used in f-strings, or the way colon equals is used in assignment expressions. This is a totally different thing. It's equals and then the colon. And this actually automatically prints out the name of the thing that you're evaluating into it. So I can use the same exact format specifier, but I don't have to put math.py equals in there an extra time just to get that out in my string. So not only does this make it easier to debug your Python code because you don't have to write as verbose of an f-string to do it, it also really helps for debugging f-strings themselves, since all you have to do is add a single equal sign and you don't have to worry about messing up the rest of your string. Yeah, so I think that's really nice. In Python 3.8, several additions are being made to the typing module, which provides standard type annotations to be used by third-party type checkers like MyPy. These are generally used with function annotations added in Python 3 and variable annotations which were added in Python 3.6. So here's a toy example if you're not familiar. I define a function foo. I say that its first parameter is of type optional int, which basically just means it can be an integer or none, and that's the only things that are valid. And I say y is the union of string and bytes, meaning it's either a Unicode string or a byte string. And this function always returns an integer, as you can see at the far right of the screen after the arrow. And then inside this, I define a variable z, which calculates a value and is always an integer. So let's talk about the new types that were added: literal, final, and typed dict. First, typed dict, which here I'm defining a class movie, which is going to be a dictionary with 2 different keys, and typed dict allows me to say specifically what type I need those keys to be. So I say the name of the movie has to be a string, a Unicode string, and the year I want to be something very specific. I've decided I only like movies that were made in 1982. So I'm saying that the year has to be literally 1982, the integer, and no other value is allowed here. And then I define an instance of movie, and I say that it's final, meaning I don't want this to ever be changed. So instead of just saying movie : capital M movie, in its type annotation, I say final movie, which means that it can never then be changed. And I define a valid instance of that, where Blade Runner is the name, which is a string, and 1982 is the year, which is the year we said we like. And then on the next line is where all the action happens. I violate every single rule I just said. I redefine movie after I said it was final. I say the name is 1984 as an integer instead of as a string, and then I say the year is 1984, which of course is not 1982, so I don't even know why I would care. And the way most people would verify a type annotation like this is running it through MyPy at the command line or during CI or something like that. And so without going into too much detail on what MyPy is and how it does, you can see here we get our expected errors. At the top, you see we get an error for trying to assign to the final name movie. In the middle, you can see that typed dict is saying that we have incompatible types for one of our keys, specifically that 1984 was of type integer instead of being of type string. And finally, we can see that typed dict is saying that the literal type wasn't matched. It expected to get literally 1982, and it got 1984 instead. So all 3 of those are working as expected. So the typing module is really cool. It does a lot of other things too, along with MyPy and other third-party type checkers. And you should check it out and maybe watch an old talk of mine called Function Annotations and Type Checking that I gave at PyOhio back in 2015. In older versions of Python, the keys in a dictionary were not in any specific order. It was sort of arbitrary and implementation dependent. So there was no real idea of iterating over them in reversed order because there was no order to reverse. But in Python 3.7, dictionaries now keep their keys in their insertion order by specification. So now the idea of going over them backwards makes sense. So as you see here, I can call the reversed iterator on my dictionary, and I get the keys back in reverse order. And I can also do the same with the values method, which returns a special kind of object called a dict view in Python 3. Now note that in Python 2, the values method and items and keys returned lists. So you actually could call reversed on them back then. It just wasn't meaningful because the order was arbitrary. So the bottom line won't give you an error. It'll just give you nonsense on Python 2. But the top line would give you an error in all previous versions of Python. So many of you are probably familiar with the Async IO library that was added in Python 3.4. And part of what it does is allow the definition and use of asynchronous methods, which can be called inside an event loop. Prior to Python 3.8, you couldn't use these methods in the REPL because there isn't an event loop running. And kind of you still can't. On the left, you see the old error in older versions of Python 3 after 3.4. And on the right, you see the new error. It went from invalid syntax to saying await outside of a function, which is nice, but you still can't actually do it. But actually, you can. Python 3.8 adds a new feature where you call Python with the -m flag and the module name async IO. And async IO does the event loop stuff for you in the background. And it starts up, it prints out some messages about the version of Python you're running and how to get help, which I've deleted here. It says to use await directly instead of async IO to run, and it imports async IO for you. So that all happens automatically. I didn't type any of that. And then you can define your asynchronous function and call await on it right there at the REPL. So this is really great for exploring these new methods that a lot of people, or these new keywords that people aren't familiar with, and helps you debug simple cases in the REPL, just like you would for any synchronous code. So now in the less than 5 minutes I have remaining, I'm going to talk about a few features that it's likely most of you will not run into in the next 5 years. Everything we talked about so far, yeah, good chance you'll run into at least most of them in the next 5 years of writing Python. These you're probably not going to, but they're used internally by Python in the libraries that you use every day and by C extensions. So I think it's still interesting, but if you're watching this later on YouTube or reading the slides, you can skip this part if you don't care. So people have tried many times to make it safe to run untrusted Python code without crippling Python's core functionality. But eval and exec and compile and other dangerous features are used internally within Python, the standard library, so that's really hard. So what's been done in Python 3.8 is adding some hooks that at least let you audit calls to those dangerous functions, even if we can't figure out a good way to only let them through when they're safe. So we can add a hook using sys.addAuditHook and a callback, and then we can log audit events using sys.audit. So as you can see here, as soon as I add an audit hook, because I'm at the REPL, I immediately get back an audit line saying compile. And then later, if I call sys.audit manually, I get back 3 events, one of that line of code being exec'd by the REPL, one of the event that I'm manually logging, which is just a name and then a list of arguments. That's the signature of that callback and of sys.audit. And then finally, that weird compile again that I don't actually understand. There's actually a second hook, but since you can only set it from C, I'm not going to talk about it here. But it's called when you open a file containing code that you intend to run from within Python. There's one unusual thing about this PEP, which is that it's actually copyrighted and distributed under the open publication license. Every other PEP that I've seen that I remember, and every other PEP that's talked about in this talk, are all in the public domain. I looked into this license, and it was abandoned by its creators, and as far as I can tell, everyone else, like 10 or 15 years ago, in favor of the Creative Commons licenses, which are widely used, including notably in Stack Overflow answers, and I think by Wikipedia. So I don't know why Microsoft decided to do this. If anyone knows, come talk to me after. I'd be curious to know why they didn't use something better vetted legally or just release it in the public domain like every other PEP. So the last 2 things I'm going to go through really fast. Pickle is a way to load and save Python objects. And in Python 3.8, there's a way to save big buffers of data that are basically just views into C memory really efficiently without a bunch of copies. And so this is something we can use in the future to avoid having to use third-party serialization formats and still be really fast at sending data between Python processes versus the way this used to be used, which was to write to disk. And finally, there's a new way to call functions called vector call. There's an old way to call callable objects in Python called tpcall. It creates a lot of intermediate objects, but it's general, so it can be used everywhere. Internally within CPython, there's something called fastcall that skips all that and is really fast, but it wasn't available to like C extensions or to Python types and classes. So vector call allows that to happen. So you'll see like range, list, string, and type over the next couple years be modified to support this and be called much faster, as well as third-party C extensions being able to take advantage of this. For now, no performance benefit, but a lot to come in the future. So that's all I've got for you today. These are my favorite features in Python 3.8. I encourage everyone to read the official What's New page and to dig into the PEPs and bug tracker issues for these and the other features if you're interested in learning more. Almost the entire content of this talk came from those places. Some of these examples, probably even some of the words unintentionally. If you'd like to get in touch, you can find my contact information and these slides on my GitHub. The slides will also be available on the PyBay website, and the video will be on YouTube. And if you have any questions, I'm glad to take them in the hallway after the talk. Thank you very much.